All right, so welcome back to the second hour of our day focusing on randomized control trials with time to event outcomes. I am delighted to introduce our next speaker, Dr. Helene Rydgaard at the University of Copenhagen. Her research interests are in the fields of causal inference, time to event analysis, and machine learning. So again, a great match for this, this consortium, this collaboration. And she's really focused on exactly what we're talking about today, the use of data adaptive methods for drawing valid causal conclusions, both for RCT data and for large-scale time-varying observational data. So without further ado, I'm delighted to hand it over to you, Helene.
Thank you. I hope everyone can hear me. I'll just share my screen.
Yeah, you're good.
Nice. So, okay, can you see my slides now?
Yep, looks great.
Okay, good. Okay, so you just heard David talk about TMLE for discrete time survival analysis. So I will now tell you about TMLE for continuous time survival analysis. So we'll talk a little bit about doing this targeting, also superlearner and the so-called highly adaptive lasso. So you'll probably recognize many elements from David's talk. In a sense, I'm taking a step back, taking my offset in Cox regression, and then I'll try to show how we can build TMLE on top of that and what we can gain if we go all the way. So yeah, just as an outline of my slides here, I'll first try to clarify this discrete to continuous time, give a general introduction to my setting. Then I'll review this roadmap or the statistical estimation problem that we're interested in here. Then I'll talk about targeting and then incorporating these machine learning tools. And then I'll just finish with some concluding remarks. Right, so continuous time TMLE for survival analysis. Well, in essence, it's just about combining the right things. So as Maya has talked about, and David also, we're targeting these causal parameters. So parameters that arise through this decomputation formula. And then we have these existing TMLE for survival and competing risk analysis in discrete time. And they're example of methods that go after semi-parametric efficient estimation in a nice way that allows for incorporation of these machine learning tools, such as superlearning and highly adaptive lasso. So it's just basically what we want to combine together to construct a TMLE for continuous time survival analysis. So in this approach, will be based on multiplicative hazard models in essence, and then I'll put special emphasis on these Cox regression models today. So first of all, just what do we mean, or what do I mean by continuous time? So we're just considering a standard setting where subjects can die on any given day. The subjects can be lost to follow-up or right censored at any given day. And then in a more general setting, which we'll not consider today, then subjects can also start or stop treatment on any given day. So the practical motivation for this is that we need something for the data settings where this optimization that David talked about will not run because time is essentially too fine. So the general data structure that we take is one where we have a line of data or a row of data for each individual. And then we'll have this time t tilde till event or censoring. So now this is taking value on the positive real line rather than on some discrete set of times. And then we'll have an indicator delta indicating event or censoring at this event time, a binary treatment variable indicating treatment or no treatment, and L, a vector of pre-treatment covariance. So the difference between this and what David talked about is where the event time takes its values. Right. So as we've seen a couple of times now, then this general TMLE template consists of two steps: the initial estimation step, and then this targeting step or targeting algorithm. So we want to apply that to this continuous time survival analysis setting. So one of my points here with this talk is I basically just want to demonstrate how easy it is to build on top of what we already do in continuous time or just survival analysis by applying these targeted learning principles of this TMLE template. So I wanted to start from scratch and then just show how we can go from a Cox regression approach to this TMLE estimator. So to do that in this considered setting, that will involve targeting these continuous time intensities. So the step 2 of the TMLE template, But then also to improve upon just using a Cox regression approach, also incorporate these machine learning methods for estimation of continuous time intensities. So this is a part where it gets a little harder than in discrete time, because in discrete time we can use logistic regressions, and there are a lot of different machine learning tools for estimating binary regressions. But there are not as many methods for estimation, or machine learning methods for estimation of these continuous time intensities. So we may have to be a little more creative or dig deeper. Right, so there's some nice properties that we gain from each of these steps, as Maya has also just shown. So in this targeting step, that's where we get so-called double robustness. So in essence, a bias reduction, and it also provides the basis for establishing efficiency and the basis for constructing confidence intervals and p-values for valid statistical inference. And then for these machine learning methods that we want to incorporate, we have some nice theoretical results, such as oracle selection and guaranteed convergence results. So throughout, I'll illustrate on simulated data, just try to keep it simple, stick to the same setting throughout. And then I also want to dig a bit into the technical parts. So it will be a combination of a demonstration and then also an insight into how we actually carry out TMLE, or what it takes for this setting. Right, so as I said, I will focus on just one simulation setting. So it's just completely hypothetical. So it should imitate a randomized trial. So we have a treatment variable A that's randomized at baseline. Before it was randomized, we measured covariates that are here allowed to be predicted for both events we're sensing. And then I've simulated the data such that the hazard of event has a change point. So the conditional hazard ratio is above 1 in the first half of the follow-up period, and then in the second half it is below 1. So we can immediately see that a simple Cox proportional hazard model is misspecified, and also we just generally don't want to report these hazard ratios, as we've now heard. And then another general method that we would apply in a randomized trial would be a Kaplan-Meier approach, but that's completely non-parametric and doesn't adjust for covariates. In this case, it wouldn't be able to take into account the informative censoring, as we also saw from David's simulations. So we need to focus on something that has a causal interpretation. So just here I just show the true counterfactual survival curve. So I just generated the data from each counterfactual scenario and then plotted the survival curves. So here we see that throughout the follow-up period, the control survival curve is above that of treatment. So that would indicate a harmful effect of the treatment throughout the whole follow-up period. Right, so let's get started with something that we want to estimate, or like to quantify the effect of our treatment. So I just picked the average treatment effect, or the ATE, on survival. So it's just the difference between the two counterfactual survival curves evaluated at a fixed time horizon, T0. And then I just wanted to review how we would estimate this with the Kaplan-Meier. So with the Kaplan-Meier approach, we just, in every single data set, we would fit the two Kaplan-Meier curves, one in each treatment arm, and then take the difference at time T0. But then, of course, if we repeat that many times in my simulation setting, then we see the bias due to informative censoring. So this plot structure is one that I will use again. So here on the x-axis, I have the target parameter scale. Then I've marked the true value by this dashed line. And then we see the true value indicates a harmful effect. It's below 0. And then the Kaplan-Meier estimator, the empirical distribution of the estimates is shown here with the solid line showing the quantiles across the simulations, and then the point just showing the average. Yeah, so the Kaplan-Meier is biased, just like we know it would be. So we need to take covariate information into account. So without going into too much detail on this identifiability, I think David talked nicely about it. So we need these different causal assumptions, essentially, to go from the counterfactual world to a statistical estimate. I'll just focus on the statistical estimate. So what we can know is that under these identifiability or causal assumptions, consistency, non-measure confounding, and positivity, that we can represent the counterfactual survival probability as an expected value of a product integral over hazard increments, which under the assumption that the hazard is continuous, we can equally well express this expectation over the exponential function to minus the cumulative hazard. So the statistical target parameter only depends on data generating distribution P through the hazard or the hazard increments. So what we can note from that is that, first of all, this outer expectation that's over the marginal distribution of the covariates, we can estimate that by the empirical distribution. So what remains is this hazard or the hazard increments that are now an ingredient in constructing an estimator for the target parameter that has a solid interpretation. Right. So what we need is an estimator for the hazard to proceed from here. So the question is what we assume about it. So in other words, what is our statistical model M? So as I said, the basic Cox model would be specified, but we could specify it here. So just including a main effect from treatment and covariates, and leaving the baseline hazard completely unspecified or unrestricted. Another option here is that we know that there is this change point in the hazard. So of course we would need to take that into account to get consistent estimates in the end. But then there are also a bunch of other choices, because essentially we don't know if there are interactions in the data, or maybe there's a squared effect of some of the covariates. So let's just start out saying that I know the true Cox model, which I do, and then I estimate the target parameter based on that Cox model fitted to my data. So the same plot as before with the Kaplan-Meier estimator, and then the Cox model that's correctly specified nicely corrects that bias of the Kaplan-Meier by taking into account the covariates. But then if I misspecify that Cox model, here I just left out that the change point in the hazard, and then I also misspecified the functional form of one of the covariates, I get something that's very biased. And here it's even showing the opposite effect of what the actual effect is. So the actual effect was below 0, indicating a harmful effect. And now this misspecified Cox model gave an estimator for the average treatment effect that was actually above 1, indicating a protective effect. So to do better than this, let's get started with this target estimation framework. So we want to move beyond relying on the hazard model being correctly specified. So basically our goal is to enlarge this statistical model M while still ensuring valid inference. So another thing we can note is that we don't actually care about the hazard. We care about the target parameter and want to optimize estimation specifically for that target parameter. So in other words, we want to go after efficient estimation of that target parameter. So it's a result of superparametric efficiency theory that efficiency and asymptotic normality of a plug-in estimator for the target parameter relies roughly on these two conditions, where the one is that the estimator solves the efficient inference curve equation, and then the other condition is that a certain second order remainder converges fast enough to 0, or is OPN to the minus half. So these two conditions in essence tell us what we need to estimate and how well we need to estimate it to get optimized estimation for the target parameter. So the rough idea of TMLE is exactly to design or construct an estimator such as to fulfill these two quantities. And then once we have it, then we can compute confidence intervals based on the efficient inference function. And also the estimator will have the smallest possible asymptotic variance given the model M. So we need to dig into what these two things are. So the efficient inference function, David also presented it, now just for continuous time instead. So the main difference is just that the finite sum over time points in the expression that David had is now this martingale integral over time. But it's still the same dependence on the conditional hazard, the censoring mechanism, and the treatment mechanism. So that essentially tells us that to construct an efficient estimator, we need to estimate all of these three quantities. And then an estimator, P hat n, consisting of an estimator of these three quantities, well, we say that it solved the efficient inference curve equation. If we plug those into the expression for the efficient inference curve, take the empirical average, and then we get something that's roughly 0. So that is what the first condition was. The second condition was about this second order remainder for the estimation problem. So we can derive its exact form for our particular estimation problem. So without going into too much detail, what we can note is that it displays this nice double robustness structure. So basically it factors into these two parts, where one is concerned with the censoring and also the treatment mechanism, and the other part is concerned with the event process mechanism. And that implies two nice things for our estimation problem. One is that this condition on the second order remainder being OPN minus half, that translates into an n minus quarter convergence rate for each of these two parts. That will be essential for incorporating machine learning methods. And then another thing is that this is what we usually call double robustness or double robust estimation, is that consistent estimation of the target parameter will only require consistent estimation of either the censoring or the event process distribution, or the survival distribution. So I thought that I would focus on that last thing, just to introduce the targeting step and just display what it achieves. So again, TMLE consists of initial estimation. We construct initial estimation meters for all components of the efficient inference curve. Then the second step, the targeting step, where we update an initial estimator specifically for the hazard of event, such that we solve the efficient inference curve equation. So for example, just to get started now, we can use a misspecified Cox regression model for initial estimation of the conditional hazard. And then in the targeting step, they will be updated using the information from the estimated censoring and treatment mechanisms. So I'm going to assume now that we have those estimators for the censoring and treatment mechanisms. And then let's take as our offset this misspecified Cox model that had a very biased estimator for, or provided a very biased estimator for the target parameter, the average treatment effect on survival. Right. So targeting a continuous time intensity, what does targeting in general take? Well, we would need the efficient inference function. We have that. Then we need an fluctuation model for updating. And then we need an actual updating algorithm. So here we'll go for a fluctuation model for the conditional hazard. So takes the given hazard and then multiplies by the exponential function to some parameter epsilon times a clever choice of a covariate h. So in this model, we would move away from the hazard itself by varying this epsilon, and then we would move along a path defined by this clever choice of a covariate h. So the clever choice essentially just depends on the structure of the efficient inference function. So if we look at it again, here presented once more, we just read off what this clever choice should be. So what we can note immediately is that it depends on the survival function, the treatment mechanism, and the survival censoring survival function. So this is where that information is taken into account through that that clever choice of a covariate h. So now the idea is that an optimal fluctuation epsilon hat is computed such that we have an estimator for the hazard. We plug that into the fluctuation model, we evaluate it at this optimal fluctuation, and then we solve the efficient inference curve equation for a given estimator for the clever covariate. So it's just about solving an equation, a score equation in terms of these martingale intervals that enter into the efficient inference function. And then we iterate that process until we solve the efficient inference curve equation exactly. Right. So let's just show how that plays out in a given data set, just to get a good feel of what's actually going on. So here, down here on the real line, I have the true value of the target parameter here expressed in terms of these cumulative hazards. So now I can provide an initial estimator for the cumulative hazard based on my misspecified Cox model. Use that to provide an estimator, plug in an estimator for the target parameter. This was biased, so we get an estimate that's quite far from the true value. Then I apply my fluctuation model to update the initial estimator for the hazard, shown in the previous slide. I get a new estimator, then I can plug into the expression or to the to estimate the target parameter. Now I get a new estimate after the update step where that discrepancy has been removed from the initial estimator. So that was just one of the simulations, just to show. Let's look at how it plays out across the simulations. So I had the misspecified Cox model with a large bias. Now I just applied the TMLE step on top of that. And we see that completely like we would expect it to, then it removes this bias entirely. So we can also look at like relative mean squared error. So how much precision did we gain compared to the Kaplan-Meier? And here we see that we gain a little bit of precision because we did take into account covariate information in specifying this Cox model that was misspecified, but we're not really taking it fully into account because it was misspecified. But then there is another thing we can know is that here I provide the coverage based on the efficient inference function. So this is actually nicely 95%, even though that's not really guaranteed by theory. So just to conclude on that slide, TMLE removes bias from the initial estimator, but then the better the initial estimator, the more precise the estimator for the target parameter. That's what we know. So we can do better than just applying a misspecified Cox for the initial estimation. So let's get started with this second part, incorporating machine learning for the initial estimation. Let's focus on this other part. We want to enlarge the statistical model while ensuring valid inference. So we want to do it, incorporate these flexible methods, but in a way such that we can still establish that the second order remainder is estimated fast enough. So we saw earlier that condition on the second order remainder can be translated into convergence rate for each of the nuisance parameters of the centering mechanism and the event mechanism. So those should be estimated faster than n to the minus quarter. And that will be crucial for using these machine learning tools. But given that we have that, then we can again conclude efficiency and asymptotic normality of our estimator, and we can compute confidence intervals based on the efficient inference function. And our estimator will have the optimal asymptotic variance. Yes, so let's get started with superlearning, or just go over it very briefly. So instead of using a simple Cox model for initial estimation, we could apply a superlearner approach where we just propose a large selection, or a so-called library of Cox models, and then use cross validation to pick the best one. So in practice, that would incorporate the V-fold cross validation scheme, where we would split our data set into equal size disjoint samples, and then in turn use each of these samples as a validation sample and the remaining samples as training samples. Then in each of these folds, use the training sample to construct the estimator and the validation sample to evaluate the estimator. And then based on some choice of a loss function, we can now define the superlearner as the estimator that minimizes the loss-based cross-validated error. So this is an honest way of asking the data which model performs best. And particularly, we should note that the loss function will now determine what is the best model, which model performs best. So we should think about that when we specify the loss function. So yeah, we can construct, for instance, a superlearner for selecting between different multiplicative hazard models. So all models on this form, factorizing into a baseline hazard, left unspecified, and then the exponential function to a function f of t, a, and l. So in this case, we note that the likelihood is proportional to this factorization into the hazard increments at the jumps of the counting process, and then the exponential function to minus the cumulative hazard. And then just a standard profile like likelihood argument, just say that for fixed f, maximization of this equation leads to the Nelson-Olin estimator for the baseline hazard increments. And then when we insert those into the equation 1, then that yields exactly the Cox now profiled interpretation partial likelihood function for f. And then we can now use that one to compare different models for f when lambda is of this particular form star, and we use the completely non-parametric Nelson-Olin estimator for the baseline hazard increments. So that now means that we can construct a superlearner that now does model selection for us between a library of different pre-specified Cox models. So those could incorporate different time-varying covariates, such as the change point for our purposes here, and also different functional forms or different interactions between A and L. And then we would ask the data which one would perform best for us in an honest way. Right. So there are some theoretical results for this superlearner. So under some conditions on the loss function, then the so-called oracle inequality applies and says that the superlearner is asymptotically equivalent with the oracle, the best estimator in this library. And that particularly means for our purposes here that either we assume that one of the Cox models that we used in our library of estimators is correctly specified, or we ensure that one of the included algorithms attain this critical into the minus quarter convergence rate. So if we don't want to claim that in our Cox models that's correctly specified, then we can construct a superlearner that includes the so-called highly adaptive lasso of the Hall estimator in its library. So put shortly, this Hall estimator is a machine learning algorithm that basically requires no parametric specification. So it's guaranteed to achieve this convergence rate into the minus quarter under just the only assumptions on the true function is that it's Catholic, so it's continuous from the right and has limits from the left, and then it has finite variation. So in essence, the true functions can be discontinuous and have jumps as long as we ensure that it's not having infinite jumps in small intervals. Right. So just to put a few more details on this Hall estimator, well, the basic idea is to solve this infinite dimensional estimation problem where we minimize the loss-based empirical risk over the entire function class of Catlett functions with the variation norm bounded by a finite constant m. So yeah, the idea is that with the Hall estimator is that we solve this infinite dimensional estimation or minimization problem by approximating or representing the function in this function class by a linear model in a very large number of indicator basis functions. The nice thing is that in practice, we can compute this Hall estimator by the su-penalized regression, where indicator basis functions, the indicator basis functions are treated as covariates, and the point mass assigned by the function to the support points of the observed data are the coefficients. And then the variation arm will be equal to or approximated by the sum of the absolute values of the coefficients, which is exactly the L1 norm. Yes. Okay. So this Hall estimator is already well defined for regression and binary regression problems. So we need to define it for the continuous time conditional hazard. So just a few considerations on that. So we propose to parameterize the conditional hazard into two functions that are cat-like with finite variation. So the true hazard has this form. It's given as the exponential function to the sum of these two functions. So if we, for instance, specify f1 to be log the baseline hazard, then we're exactly back to the form that we had before for multiplicative hazard models. So now a Hall representation for f1 will be in terms of indicator basis functions for the variation along the time axis, and a Hall representation for f2 will be in terms of indicator basis functions for the variation along covariate axis. And also for time and covariate and treatment interactions. Those could be two-way interactions, could also be three-way or etc. And then the overall idea is that bounding the variation norm corresponds exactly to bounding the L1 norm. So that controls the smoothness of the resulting function by controlling, for instance, how many indicators will receive non-zero weight. And then, just as a side remark, we would use cross-validation to data adaptively select this bound on the variation norm. And then by the oracle properties of superlearning, we would just need one of the considered bounds to be larger than the two bound, and then that would be good. Yes, so a little more considerations on this implementing a Hall estimator for continuous time conditional hazard. So just very briefly, the theory points to using this completely non-parametric Nelson-Nolan estimator for the baseline hazard. So in essence, this is like not penalizing the time indicators for F1. So we could go for two different options here, using a whole representation for F1 with a parameter for each observed event time, or use the actual Nelson-Nolan estimator. So if we go after one, we can use the super-penalized Poisson regression. And we have the option to penalize or not penalize these time indicators. If we go after two, then we can use the super-penalized Cox regression. Yes, so here are just some results from applying a very simple implementation of this whole estimator and then putting the TMLE step on top of that. So just compared to, I've also included the estimators from before. So we had the TMLE based on the misspecified Cox, and now here at the top, I have the whole TMLE. So again, nicely unbiased estimator for the target parameter. A nice coverage, which is in correspondence with the theory. And then we see that the relative mean squared error compared to the Kaplan-Meier estimator is decreased compared also to the TMLE with the misspecified Cox. So what we see is that this whole TMLE can improve precision just without any model specification. So it just data adaptively finds the covariate information to take into account, including this change point in the hazard. So what it provides in the end is the right combination between flexible estimation and then valid inference and optimal inference, in a sense. Yes, so that was about what I had, just some concluding remarks. I've tried to show here that we can improve a simple Cox regression approach by adding this targeting step. But then we can also improve a simple Cox regression for initial estimation by combining different Cox models into a superlearner. So essentially, the superlearner provides an honest way of doing model selection, where we can even make sure that the model selection is using a measure that also is optimized for the target parameter. But then we can also improve this superlearner of Cox models. We can, for instance, include other models that are much more flexible, such as CoxNet. But then we can also use this highly adaptive lasso estimator, which really stands out because it achieves this n to the minus quarter convergence rate while still being very flexible. So in the end, if we're willing to go all the way, what we can achieve is this fully data adaptive Hall TMLE for continuous time survival analysis. Yeah, so I hope I've been able to show that we can use these principles of the TMLE template to construct a TMLE for continuous time survival analysis that included this targeting along this multiplicative fluctuation model, and then there are different options in the construction of superlearner and the libraries and the whole estimator. And then just on a very final note, I just wanted to mention this is this setting considered here is a special case of other settings of our ongoing work on this continuous time TMLE. So a more general setting would be the one that incorporates these time-dependent treatment and confounding. And then also the setting we consider today, we also have similar work on the competing risk setting, targeting average treatment effect or just general treatment effects on the absolute risk function. And then we're also very interested in these general dynamic and stochastic intervention. Yes. Thank you so much for your attention. That was what I had.
Thank you, Helena. That was fantastic. Great talk. So we do have a few minutes for questions. Go ahead and type them into the chat. I know last time it took a moment for people to process and formulate their questions. In the meantime, we have a question that was asked in the last session we ran out for, so we will go ahead and address it now. And I'm going to send this one to Mark. So the question is, if the superlearner has been pre-specified, what do you do if it does not converge?
Yeah, sure. So this concerns that some of these algorithms in your library might in certain settings not converge. I mean, one of the settings is actually already logistic regression, right? It has sometimes issues converging, certainly if things get sparse. So this is actually one of these things. Now, number one, you want to program the superlearner in a way that if one of the algorithms doesn't converge, that it should just drop it, and then just work with the remaining algorithm to choose the best one. But really, this also gets to the setting up the statistical analysis plan is that it's important to run your actual TMLE in kind of the similar data as you're going to apply it to make sure everything is working properly. Because it might be exactly that type of situation where things are just too sparse and that's, for example, on logistic regression has trouble converging. And that's something you can address at that point by making sure, that you don't have too many variables fitting a logistic regression when the sample size doesn't warrant that. And these kind of things are typically the reason. And then there are also algorithms like neural networks, which are weird in other ways. You can apply them to the same data multiple times and every time get a different answer. So that's really a randomness in the algorithm itself. Anyway, the superlearner doesn't care. It just, but that's something to be aware of. I think that's about it.
Great, thank you. So we have another question. How computer intensive is your method? Would it be feasible for a large scale registry study? So maybe we'll go to Helena first and then David and anyone else who want to make comments.
Yeah, so I'm assuming we're talking about the method that I just presented. So that will depend on which part you would be interested in because like the targeting step is fast. And the superlearner combining these Cox models is also very fast. The whole, on the other hand, in my current implementation is not fast, but that's of course something that we can optimize along the way. I hope that was
great. Yeah, that's great. And maybe just a very brief comment from you, David, as well, and then Mark, and then we'll move to our final speaker.
All right, yeah, so for the discrete time implementations, this depends on what models you put into your superlearner library for estimating conditional hazards. And it also really depends on how many time points you're interested in estimating survival probabilities at. So the answer is it depends. Sorry.
That's great. Maybe Mark, any brief concluding remarks, and then we will move on to our last speaker, who is you.
Yeah, no, quickly is that for the nice thing about the continuous time is that if indeed there are many time points, and that could be approximate even continuous time, then the kind of discretized time TMLE, which is based on running pooled logistic repeated measures regression, starts essentially applying a logistic regression to a huge data set, right? As many time points times the number of individuals, and it becomes therefore slow. On the other hand, the continuous TMLE Helene talked about doesn't have that problem at all. So it's actually very fast still, and it's not affected by that. So that's and that helps immensely then with the computation time. And then regarding superlearner, again, it all depends on the kind of algorithms you throw in there. And that's again something with an a priori study. You might see, hey, for this type of data, I don't really need this type of algorithm. And maybe make it more scalable in that way.